Welcome everyone to our 4th day of the winter school. I see 9 o'clock still works. And of course we're having the beautiful day for our excursion later. So the weather waited for that. Usually it's a bit nicer here, but yeah. So today we will start with human-aware navigation, where I am, so Chris Reinke. I'm a part of the INRIA team here of this SPRING project that you heard about all the time. And I will start with showing you a little bit about what algorithms we are using, and that also gives you an idea of what's out there, what is the normal classical control to have these mobile robots moving around. And afterwards we will then hear from our invited speaker, Xuesu, a bit more elaborated algorithms, how to improve upon this standard. So let's start. So what is our task if we think about mobile robots and social robots especially? And that is that, of course, we would like that the robot, so here we have our ARI robot. It navigates from a point A to B. Here it will navigate to Xiao, that is standing here. But of course, it has to take into account humans and also groups of humans. So it should not get too close. It should not intervene, go through a group of humans. But we would also like that the robot has some knowledge about how does it optimally join a group of humans to start an interaction. And maybe it also has other tasks like how do I follow a human or how do I guide a human. So these are all tasks that fall into this category of human-aware navigation. And so here we can look how this, I would say, the classical framework looks. So this most probably 95% of all the robots that do mobile navigation will kind of use this. It's again boxes. So let's start at the beginning. Here are our inputs to our navigation system, and usually you will get a map, which is it's called the occupancy grid. So it's basically mapped before you do the navigation. And it shows you in the black dots what are my obstacles, so what is occupied. In the light gray, we're having our free space, so where the robot can navigate around. And in gray, dark gray, we're having the unknown space, so we don't know about this area. So that's one input. Of course, we would like to know where is our robot, so like in the X, Y, and maybe its angle coordinate in this space, in this map. And especially for us in social robotics, of course, we would like to know where are the humans and also with their orientation. So this basically is then given to our framework, and our framework consists usually out of two components. One is the global planner and the other one is the local planner. And the global planner is more responsible for the course planning. It basically tells you if I want to go from this room to another room, and it gives you some waypoints, so how to achieve this, and we will come to this in a moment. And based on these, for computing this, it also uses usually kind of a cost map, which tells it, you know, what's the optimal path in terms of a cost function. Usually that's not too complicated. And then these waypoints are given to the local planner, and the local planner does then an actual fine-grained plan to go between these waypoints. And for this, we're also using, again, a cost map, but this is usually then a bit more elaborated. So here we, at least in our project, here we having then, for example, the humans also coming into play. And the local planner then creates your motor actions, of course. So let's have a very brief look to the global planner. As I said, it creates a kind of high-level navigation plan. So we just create kind of a series of waypoints, so here in blue, to our goal in green, that then the local planner will achieve. And for this, we usually do some simplifications of the robot model. So we think, for example, the robot is maybe only a circle or an ellipse. So nothing, you know, very complicated, so that this planning is easier. And we definitely often don't take into account any dynamics of the robot model. So what the robot can really do, like like what curves can the robot really drive. So we don't think about this too much. And for this planner, there exists actually like a large amount of algorithms. So here is one of them, just an illustration. It's called fast marching tree. And this works that we're starting in our, where the robot is at the beginning, the blue point. And then this fast marching tree, it generates kind of a tree of where the robot could go. It's kind of a random, you know, it creates these random possible paths outwards. And then from the end locations of each of these branches, it then starts in the next iteration again to go outwards. And what we hope is then that at a certain point in time, we reach our goal. And if we do this, then we can basically follow these branches that reach the goal and create our waypoints on that way. So it's a very kind of simple algorithm, but it usually works fine. So then this is given to the local planner. So now the local planner gets the, let's say, like the local planner knows it's here and it has to go to this next waypoint. And the local planner can actually take into, or usually takes into account a bit more elaborated or realistic model of the robot. So, you know, you can describe the robot a bit more in detail and also of the environment. And so here we will talk about two possible solutions. The first one that we're also using in the project is model predictive control, and that is a planning algorithm. So everything gets planned. You give it the map and it plans in the map. A second solution, which we are currently also working on, is deep reinforcement learning. And here you learn to navigate. So it's not anymore planning in that sense. So let's start very briefly with the model predictive control. So we have a few formulas, but I won't go into details. So in model predictive control, the idea is that we create an objective, so this function j, which we would like to minimize. And this objective has as input our S0, so S is the state of the robot at its time point 0, so where it's currently. And we also give into it the S star, which is the goal state, so where we would like to go. So you can see, and for us, this is basically its X and Y coordinate and its orientation. We're also having this alpha term, but this is just because RE has the head, and the head is, you know, you can also formulate a goal of where should the head be. And so these alpha terms are all about the head, so we can forget about this at the moment. And what we also give into this objective is, of course, our action plan. So U are our actions that we can execute on the robot. And so in our case, this is, for example, V, like a forward velocity, and W here, it's the angular velocity. So how much does the robot turn while it goes forward? And we would like to find an action plan U that minimizes this objective. And the objective is then formulated in form of these loss functions. So we have here L and R. And you can see L is kind of takes into account the state. So usually that thinks about how far am I still away from my goal, S prime, S star. But you can also have a term that takes into account the actions. So that would be something I would like to maybe use actions that use less energy, and that you basically create a cost function based on that. And you can see we then basically look into T time steps into the future. So how large is this cost? And this is what we then would like to minimize. For this, what is important is that we try to optimize, minimize this function here by taking into account the system model. So the system model is how does the robot react to an action. So this is how is the next state, depending on my current state and the action U. So for us, this model is relatively simple, but it can be a bit more elaborated. You can also add some constraints, like for us, the constraint would be on, we would like to do actions that are too fast, for example. And what you then do is there are again several methods to minimize this function. So one would be, again, you kind of maybe create several trajectories, and then you measure how is the cost for these different trajectories. And then you simply choose the one that is the lowest. So that would be a very simple algorithm, but you can do a bit more mathematical shenanigans to make this better. Yes, so basically this is then what you do. You minimize this function, you take your first action that the function tells you, and then actually model predictive control in the next step. We don't follow the next action that our function told us for the trajectory, but we remodel the whole thing again. So we optimize the whole thing again, and we take again the next action from this optimization. By this, you are always updated with your current state and getting a more optimal path. Yes, so, and what does this take into account? So these cost functions that I talked about, what would we like to minimize? So often this is, of course, collisions. So you don't want to bump into like a table. So you can see here the table. So the cost function can have what you don't want to bump into objects. Maybe the distance to goal, you want to minimize this. Maybe you could also add energy usage, but for us important is to take into account humans and groups. So, and for this, we usually fall back to these psychological, relatively simple measures of one is proxemics. So this is by Hall in '68. And proxemics is basically just tells you humans have a space, a personal space around them. And we would not like to interfere with this very intimate or personal space, but we would like to be in the social space. And the other idea comes from F formations that was introduced by Kendon in the 90s. And that is how groups are formed. And so here the idea is that if you have a group, then usually you have a R space, which is the space outside the group, a P space, where are the participants of the groups, and an O space, which is inside the group, which you don't want to interfere with. And of course, you can create these different formations that exist, but usually for a robot, you can just simplify it by having this very simple shape. And based on this, we kind of create these, we model these spaces. And here we're using a very simple model, which is based on Gaussian-like functions. So you can see around each human, we have this Gaussian-like function that goes away with the cost for entering them or going close to them. And we're also doing this for the group center. So here we have the group center. We have its space, and because of this, the robot then does not want to go through here. So it instead goes around. We can also use these models to identify how do we approach a person. So here's a very simple approach, also by Truong. If you have a space and you would like to go to these two people, you first create a circle around them of possible points. Then in the next step, you look which of these points on the circle are actually visible for the humans. So then these become your target points. Then we cut away still the parts of the circle that are interfering with the social personal space of the people. And what you are left with is like two, you can see here, like two parts where you could make an approach. And then, of course, you choose the one that is closest to the robot and like the middle of this. So it's a very simple and straightforward algorithm in that sense. Okay. So, and with this, basically, that's what we use on the daily, or in the hospital for the robot, actually, to do all these navigations, taking into account this group here. So you can see, now it's gone, but there was like a group center. That's what we do. But we're also looking into reinforcement learning for this local planner. And here the idea is, instead of having a planning algorithm, so that at each step, I told you the NPC has to plan again, next step, planning again, which costs, of course, resources. We would like to have an agent that learns a policy. And for this, usually you can use reinforcement learning. And here I will give you a quick introduction. So the idea in reinforcement learning is that you have your agent and it interacts with the environment. And it does this interaction by trying to optimize a reward function, so to maximize rewards. how does this work? So here's a very, very quick introduction. So we model our tasks, so our environment in form of Markov decision problems, where you have states. So I can be in the state here. You have actions. I can go from this state to my next patches. And then we're having a reward function. So maybe at a certain point in my problem, I can get rewards. And what we would like to do is we would like to find a policy, so basically a behavior that maximizes my sum over rewards while I go through this environment here. And we do this by learning a so-called value function, a Q function. And what we are doing here is we try to learn if I'm in a certain state and I'm doing a certain action, what is my expected future reward if I do this? And then I follow my policy that I learned so far. And then, of course, we would like to maximize. But at the core of the whole problem is always to identify or to learn this value function. So how much reward can I get in the future if I'm doing that? And for this, we can use like certain algorithms. Here's a temporal difference algorithm. What we do is, like, after the robot does a certain step, it always compares what it currently thought is the expected reward to its current observation, what is the reward that I observed in the next step, plus what it basically from the next state where it went into, what is there the maximum sum over rewards in the future again. And so if you compare this, you get an error, and with this you can then optimize your function. So that's a very, very quick introduction. Of course, we're doing deep reinforcement learning, so everything is deep nowadays. So what means this in reinforcement learning? It just means that this this Q function that I showed you here, so the expected reward, we try to approximate this with a deep neural network, whatever this network is. So here we try to solve the Atari games, and then it's some CNN layers, that can take into the image, and then it learns the value for doing certain, these actions of the controller. In our case, because all this takes a lot of time, we cannot do reinforcement learning on the real robot. So what we do is we created a 2D simulator. You can also play around with this in the hands-on session on Friday. It's basically a 2D environment with obstacles, and we also having humans here in green, and these we control at the moment with a social force model so that they can make groups, or at least they can walk and not bump into things. And then our reward function for our RL agent becomes, again, these cost maps that you saw before. So the rewards are basically now don't bump into these things, into the obstacles, and also try to avoid these spaces, to intervene with these spaces of the humans. Then our agents, they, as I said, it's like a deep reinforcement learning. So you give as input kind of your map, your local surrounding. Here are the humans messing, but you can make another thing where you give in the humans, and you give it the distance to the goal and the angle to the goal location you would like the agent to go. And then the agent, like after you have several layers, the agent tells you then what's the value for this action versus what's the L value for that action to do. And you try to learn then this. And yeah, so with this we can then basically learn, for example, object avoidance. So the robot tries, goes this path without bumping into these objects. And we also started to do human, like to taking human into account. So you see here these humans, they're walking. And the robot tries then here to not bump into them. So it especially avoided this path here of this human. But we will talk about this more. If you are in our hands-on session, you will actually try to train such an agent and to see how certain components of the algorithm interfere with this. And with this, I'm at the end of my session. So thanks. And if you have questions, then shoot.
Thank you very much for this informative presentation. I would like to ask two things. In the very first slide, you showed us about the robot performing, navigating through and approaching Prof. Xavier. Yeah. So how the robot decides when I should go through between two persons, or when I should yeah. So first is that question. Second question, I would like to know your opinion on the reinforcement learning based approaches, which uses in the backbone neural networks. So are the outputs explainable? Because we wouldn't want any. I think you got my question. Yeah. So any thoughts on that thing? Yeah. Thank you.
So for the first question, I think it shows it on this slide here. I mean, the only thing the robot takes into account is not really, it doesn't have a discrete understanding of this is a group and I shouldn't interfere with it. So how we do it is always by modeling these costs and then just try to minimize the cost. Yeah, so, like now I have a high cost by going through the space here, and so that's why the trajectory goes around. Of course, yeah, it compares the cost. But there can be situations where maybe there's more humans here and more humans here, or there's obstacles, and then the minimal path would be to go through here. For your second question, yes, they are black box models. So the neural networks are, we don't know really what they learn. We only see they perform usually nice. But that's also a problem because we don't know how they perform always. Like there can be a new situation where it maybe does something crazy and we don't know yet. Yes, of course. So I'm not too familiar with this, but of course there's always people who try to do like safe reinforcement learning, where you restrict the robot to do that it can only do kind of safe things, but it's kind of a research area from itself.
Hi, can you maybe go to the model architecture slide?
You mean with the MPC? This one? Or no, the big one.
The big one, yeah.
Yes, yeah.
No, sorry, not that one. The neural network architecture.
Ah, okay.
Yeah, so the left side like makes sense. On the right side, you start from the encoded state.
Yeah.
Okay. And then you divide into two parts. So you use the encoder for Q-learning for the state.
Yeah.
But why do you have the multi-layer perceptron? And then why do you concatenate all of that into like one large vector or string?
So this is more a question for Victor. But I guess here we're having the our actor. That's correct. Yeah. So basically here we don't do only value-based reinforcement learning. So we're only learning a critic, because that only works usually if you have discrete actions. Because if we think of our, where is it? No. So in our Atari games, we have discrete actions. So our network output I can create for each action, like going down, pressing this button, I can create one output. And I can say, what is the value for this? But if you think of a real-world robot, you have the actions are continuous. So, I can go a little bit faster or a little bit in this direction. And because of this, we cannot have like discrete outputs of actions. And because of this, we basically have only, what we have to do is we have to give in here the action that we would like to know the value for, to then get only the value for this action. But in reinforcement learning, it's always about how do I find the maximum action. So, and for this, I have to look at different actions and to compare them. And what we basically then try to do is we try to learn a policy also, which gives us what is the current most probable highest action. So that we don't have to go through different actions all the time and have to say, which of them is now the highest, So this basically learns a mapping to what is the highest action. Yeah.
Okay, thank you.
Other questions?
Yeah.
Just to come back, first of all, thanks for the presentation. Just to come back to what he asked. So, just out of curiosity, is anyone in the team working on the explainability part of why is it choosing a certain move or?
Not, I mean, I would say not directly. So one of my research things, it's called transfer learning, and in this I'm doing successor features. And the idea there is that basically instead of learning these values directly, we learn for each policy what is my expected outcome of this policy in the environment. So how close would I get to a human? How, in which angle would I get to a human? And if you have this, then you basically can decide between different policies depending on these features. And this, of course, can give you a notion of explainability. So why did I choose that? Because then you can look, because I predicted I can get so close to a human. But of course, again, these are, so these models of, how I predict this is again deep models. So I can't really explain why they learned again what they learned. So, you are like you go one step deeper, but you still have the same problem.
I see, thank you.
We have time for one quick question. Okay.
Thank you very much, Chris. I'm going to go back to your Gaussian model of people, so not the reinforcement learning and the groups. What I found, one of the biggest problem is always that your perception isn't quite so good, and you may sometimes see this person and it disappears again. And what this often results in, if you do continuous planning, is this completely undecided robot of kind of constantly going, oh, I'm veering left, I'm veering right, there's space here, oh no, now it's gone again. In particular, while you're moving, you're also changing your perception, and you're ending in a terrible loop of robots just basically not knowing where to go. Do you do anything to conquer that, or how do you address that sort of problem of perception changing with moving and noise in the perception?
I'm not sure if we haven't explicitly had this problem too much of the robot being like, but I think we considered, I'm not sure if it's in the current model, but to use kind of a smoothing algorithm over the position of the humans. So you do an average kind of over the last time steps. So that's a very simple solution. Doesn't work again in all cases. Especially if the human moves away, you might still think the human is there due to the averaging, and then the robot does something stupid still. Good. With this, I'm giving basically the floor to our next speaker, Xuesu. So he is basically has the longest trip in terms of miles, I would say. So he's from the University of George Mason in Washington. He is an associate professor there. Assistant, sorry. We don't have these detailed differentiations here. He's from the leader of the robotics lab. Yeah, you will explain later. So yeah, he got his PhD, of course, in the US also at the Texas A&M University, and did his like master studies also in the US. But for the bachelor, you were also in Germany, so that's your European standfoot. And yeah, he's of course very active in the robotics community, being an organizer of several conferences and also editor of several journals. So it's a great pleasure to have you, and welcome our speaker.
All right, thank you, Chris, for the very nice introduction. And I'm also very appreciative of what he has showed before, and also the questions regarding safety and explainability of DRLs, because I will gonna touch upon those ideas in my slide as well. So welcome everyone. So my talk is about human interactive mobile robots. So from learning to deployment. But first of all, how to pronounce the name of my lab. So I actually don't know, but right now we converge on calling it robotics 6 because there are 2 X's at the end. I will let you know to figure out why there are 2 x's at the end. So we are from George Mason, which is right outside of Washington, D.C., which is the capital of the United States. So we are a very vibrant of roboticist group. So we call ourselves Axis Men and Axis Women, and I'm Professor Axis. I guess now you can figure out why that's the case, right? Better than Professor X, better than X-Men. So, we work on a variety of cutting-edge robotics problems. So, with the research goal of developing highly capable and intelligent mobile robots that are robustly deployable in the real world with minimal human supervision. So the robotics lab adopt a field methodology. So working with physical robots, working in the real world with actual robot end users, such as firefighters, agency stakeholders, and first responders. So our expertise is evenly grounded in both classical motion planning techniques to create capable locomotors on land, in air, and at sea, and also machine learning. So to equip those capable mobile robots with intelligence, especially the intelligence required to make them, fully deployable in the real world with as little human supervision as possible. So we are a very hardcore robotics group, so have been working on disaster robotics for a few years. So for example, on the upper left, you see this modular snake robot being deployed in the Mexico City earthquake. So highly skilled roboticists, experts, and also local responders from the Mexico City have to together drive this hyper-redundant snake robots into those collapsed buildings to search for victims. One of our previous work utilizes a overhead security camera to autonomously navigate this hyper-redundant snake robots, just as like a differential drive car, using a locomotive reduction technique. So for this Emily, this robot is called Emily. So it's an unmanned surface robot, basically a robotic boat being used in the Greece refugee crisis. So the Greece Coast Guard have to manually drive Emily from the shoreline, having lots of trouble with depth perception when the victim in the water is very far, and this is not very efficient. What we did was we teamed Emily up with an unmanned aerial vehicle, a UAV in the air. So with a visual post-stabilization technique and also visual navigation technique, so Emily is able to autonomously drive to drowning victims in the water with the visual assistance from the UAV in the air. And on the right, we show the Fukushima Daiichi nuclear disaster decommissioning. So right now, while multiple human operators have to very cautiously and also slowly drive one single packbot to decommission the power plant, so the common practice right now is also to send a secondary packbot in there. So the secondary packbot is only serving as a visual assistance, watching the first one, providing the first human crew with necessary situational awareness using visual assistance. And of course, the secondary packbot here is also driven by a secondary human crew. So imagine the increased manual labor and also the communication burden between the 2 human crews. So in our research, we replaced the secondary packbot and also its human crew with an autonomous tethered aerial visual assistance, which flies around the primary robot to provide the visual assistance to the first teleoperating crew. So this can reason about the viewpoint quality based on affordances and also reasons about motion risk in these highly constrained and confined environments using a risk awareness framework we developed. And also for safety and for resiliency and also for power, we use a tether here, and we develop a tethered motion suite so that a tethered UAV can fly around with a tether, in those unstructured and confined environments as well. So we also work on off-road mobility quite a lot, as you can see on the left. So how to drive an autonomous mobile robot on unstructured different kinds of terrains at very, very high speed, but also still maintain very high accuracy despite the disturbances from the terrain underneath the vehicle. And on the right, this is a very recent research effort from our group. So we call it wheeled mobility on vertically challenging terrain. How can we autonomously drive a very simple wheeled robot like this over terrain filled with obstacles which are comparable in size, similar to the vehicles themselves? So that's also a new research direction we have been working on. Another very important direction in the lab we work on is called mobility in highly constrained environments. So imagine environments where obstacles are right next to the robot. So the robot has to figure out how to squeeze between obstacles and without any collision, but still make sure it's collision-free and also it's fast. So imagine when you deploy those robots in your very cluttered homes or like maybe office spaces, even also after disaster scenarios as well, One of the work we come up with is called learning from hallucination. So the robot is able to imagine or self-synthesize very, very difficult navigation scenarios in hallucination, based on previous successful experiences in relatively easier ones. So I will be happy to talk about this approach. It's actually a very interesting idea of inverse, motion planning. So offline, if you guys are interested. So one of the efforts we are trying to push on this mobility in highly constrained environments is our annual BARN challenge at ICRA every year. So BARN stands for Benchmark Autonomous Robot Navigation. So our BARN, static BARN, and also dynamic BARN environments are all fully open source, and feel free to use them if you are interested in. And I also invite you to participate in our this year's ICRA 2024 BARN challenge in Japan. So, with all this very, very fancy, very, very cool research, we talked about, let's step back and think about where are robots currently being deployed? Rather than all these robots living in our fancy fantasy research world, right? So we know how to deploy robots in factories and in warehouses for decades. We have also deployed robots to vacuum our homes, and we have seen robot shows by hundreds of drones. We have also deployed robots in the medical, modern surgery, and safety and defense sector. But compared to all the robots we talked about in the last few slides in those research world, what made these robots currently deployable in the real world? I would argue that most of these robots are either being deployed in highly controlled workspaces or being deployed to execute one single pre-programmed task. But no matter how many times, but all these robots being deployed in this environment, one problem with them is no matter how many times they repeat the same pre-programmed task, they won't be able to learn anything from it, right? They won't be learn anything to deal with any changes in the greenhouse we created for them. Or no matter how many times they vacuum our homes, their performance will never improve, or they will never adapt to any new tasks. So today's robots' lack of ability to learn, actually causes a very high dependency on humans. So for those scenarios, for example, for modern surgery and also for a bomb diffusal task, we need to help from fully skilled human operators. Because humans, as we humans, like surgeons, doctors, or bomb squads, so we are able to learn and master new things in different scenarios, but not the robots themselves. So this lack of ability to learn really causes very extensive dependencies on human expertise. So although we know very well how to deploy robots in these scenarios, either fully autonomous or not autonomous with human help, eventually, where do we want robots to be deployed? So one dream, at least of mine, is we want to deploy robots fully autonomously in these kind of environments. For example, Times Square in New York City, right? But if you think about what makes a difference when we want to deploy robots in this environment, right? So can robots actually work very well in those environments now? So fortunately, there are some commercial food delivery robots on our George Mason campus called Starship. So I took these videos using my cell phone on my way to teach a class right after the last class ended. So as you can see, these robots really get stuck in many, many places in those human-populated, highly dense environments. And I kind of feel sorry for people who order food from those robots because their food will probably be very cold when they are delivered since it's taking forever. And also the worst thing is I also heard complaints from some students. If you order soup or coffee in those robots, it will spill everywhere when the food is delivered because look how jerky the robot is when facing all these humans, right? So let's think about this. So what has changed from these environments we know very, very well how to deploy robots, to these environments where the robots actually is not really doing a good job? So I would argue the biggest change here is the involvement of humans, and especially non-expert humans, who do not know anything about robotics and who are just around the robots in everyday lives, right? So in this environment, so there's no need to deal with humans. That is actually by design. We designed to put human out of the equation so the robots can work on their own jobs. And in these environments, as we talked about earlier, robots actually utilize expert human help. However, in these scenarios, robots have to deal with lots of humans. And the problem is those humans are not experts and they are not able to provide with expert help when something goes wrong in the wild, right? So this actually causes our trouble. So this contrast motivates today's talk. So human interactive mobile robots from learning to deployment. So we want to argue that humans pose, even those non-expert humans, pose both challenges and also opportunities here. So challenges are pretty obvious. We talked about earlier, right? Human behaviors are very diverse and uncertain, and safe and socially compliant human interactions in the wild is very difficult. But we also think, even those non-expert humans around the robots every day also pose a wealth of diverse knowledge that we just need to know how to utilize in the right way. And even without robotics expertise, they still present lots of opportunities. We can make our robots even better. So we are going to talk about both of them today. So we want to build human interactive mobile robots that can actually efficiently learn from these non-expert humans and also harmoniously deploy among these humans as well. So we are going to talk about first, how to utilize these very, very easily available non-expert human expertise in the field. And also we are going to talk about a few methods and tools for us to address some of the challenges in the specific problem of social robot navigation. So let's first talk about this new paradigm called adaptive planner parameter learning, or APPLE, to utilize the easily available human interactions in the wild. So the motivation of APPLE is, so if you want to deploy an enhanced navigation system in a new environment, so it's not as straightforward as they may seem. For example, you have just deployed your robots in this outdoor environment. The next deployment is in this indoor scene. So directly deploying exactly the same navigation system won't always work out, right? Also, in the same navigation environment, when the robot makes some mistakes, for example, gets stuck in this narrow doorway, more than likely the next time it comes back here, it will make the same mistake over and over again. But as roboticists, we all know that if we spend some time fine-tune the navigation system, make sure all the parameters are correct to the new environment or to fix for this very challenging scenario here, it probably will work out very well. However, this process is not trivial for people who do not know robotics. For non-expert users, this is not even possible. But our inspiration for APPLE is even non-expert humans can do the navigation task themselves effortlessly. So this is Bob, one of our PhD students in the lab. He is able to grab an Xbox controller, tele-operate the robot to go through this very complex obstacle course, even on his very first try. Therefore, the central question we want to ask in this APPLE paradigm is, can we squeeze more robust performance out of our existing navigation systems using limited human interactions and machine learning? To be very specific, so we are not trying to invent any new navigation systems, but just to augmenting existing ones. For example, this is the widely used ROS move-based navigation stack, being used on different robots. And what we did is we treat this classical navigation system just as a black box, and we stick learning components on top of it so that we will be able to give the classical navigation system the flexibility and also adaptivity of machine learning. And also very importantly, as you mentioned about safety, right? All the benefits of those classical methods will be inherited because those systems are safe, those systems are explainable, those systems can be verified to assure it's safe to deploy them among humans. So we propose to use behavior cloning to fine-tune any navigation stack. So boxes again. So let's look at this. G is our navigation system, taking some sensor input and also produce motor commands to drive the robot. This box, this navigation system, is also parameterized by a set of tuning parameters. So usually there are a very long list of them: maximum velocity, sampling rate, obstacle inflation radius, optimization weights, etc. So, and those parameters are crucial in determining the navigation system's performance in different scenarios. But those parameters are not easy to tune for a non-expert user. Those are not even easy to tune for expert users sometimes, right? So we propose to use behavior cloning to learn these parameters from demonstration using supervised learning. So this is the behavior cloning loss. We are seeking the optimal parameters here to minimize the difference between the human demonstration and the output of our navigation system G here, parameterized by theta. So the rough procedure of APPLE-D, which is one APPLE method, so adaptive planning parameter learning from demonstration here, is very simple. Collect a demonstration using a joystick, and then run any black box optimization to solve for planner parameters theta star here. So, but there's one issue here, so which we call the context problem. For example, if we use only one single star to adapt to all these different variety of environments, so humans also drive differently in these different contexts. So one single theta star may not be enough, and what we really need is a set of thetas that is able to adapt to different scenarios here. So in addition to our black box optimization on our collected demonstration, we also perform an automatic demonstration segmentation technique. to segment them into different parts. And then instead of learning one single set of parameters for the entire demonstration, we learn a set of parameters per context. And we also need to learn a context predictor so the robot knows which context it is in. And then we can actually pick the right parameters to be used by the underlying planner G. So in deployment, we basically use the sensor input and we use B5, our context predictor, to map to a context index, and the context index can be directly mapped to a set of parameters to be used in something called a parameter library. So in our experiments, we use a ClearPath Jackal robot running the dynamic window approach DW planner with one human demonstration in this complex obstacle course. So in this video, upper piece is showing the default parameters from the DWA, from ClearPath Robotics, the manufacturer of the robot, and the lower piece is the learned performance from AppleD. In the first context with curving walls, you can see the default parameters have to stop the robot many times, recompute, resample, and then go through, while AppleD learns to drive through very, very efficiently. In the second obstacle course, AppleD also drives faster than default parameters. In this curving narrow corridor, so sampling rate is increased, maximum speed is decreased. So AppleD is also to efficiently and confidently navigate through as well in a very smooth manner. And then in the last context, which we call open space, AppleD increases speed and drives straight towards the goal location, just as human has demonstrated before. So here we show AppleD works pretty well on Jackal's DW planner. But you may wonder, how about different robots, maybe running different planners? So this robot is called BWI bot, Building-Wide Intelligent Robots on the UT Austin campus. So it's running a different planner as well, called E-band Elastic Planner. So the default parameters of E-band will cause this oscillatory behavior, even this is a pretty straight hallway in the UT Austin campus. So the roboticists in our group trying to fine-tune the navigation system, fine-tune the parameters to reduce this behavior, cause the behavior in the middle. While AppleD is able to learn from one single demonstration and result in this perfectly straight line in this straight hallway without any problem. So now we know one specific approach called AppleD. So that is put the AppleD in navigation language. But we also generalize this a bit and generalize this into this whole Apple paradigm without only demonstration. So this is how we express Apple in navigation language. You have a black box, you put Apple on top, and then try to reconfigure or adjust the parameters of this black box to navigate. We can also look at Apple in a machine learning language. So here we show a contrast between end-to-end, motion learning based motion planning, like Chris has just talked about earlier using deep reinforced learning. So you have a motion policy PyM, which interacts with the physical word W using in terms of the state and the reward, and you issue raw motor commands to drive the robots. So for example, linear and angular velocity, V and omega here, right? So these actions are directly determining the safety of the robots moving in the physical world, maybe around humans. So this is probably not a very good idea because it may not be very explainable, may not be very safe, right? So that's why on the right, we show the contrast of our Apple's parameter learning approach. Instead of our motion policy PyM, we learn a parameter policy we call PyP here, which does not directly interact with the physical word W, but we devise a meta environment we call E here, which contains both the physical environment W and a classical motion planner or classical navigation system G here. So the action space is no longer the raw actions to drive the robots in the real world, but all the parameters to be used by the underlying classical motion planner G, so that the motion planner G can constantly change the parameters to adapt to different scenarios in the real world W. So this is the high-level Apple paradigm here in a learning language, right? But eventually we want to learn this parameter policy. How can we do that? Especially how do we learn that from human interactions? You already know, so this is basically the high-level idea of using some human interaction I, we should be able to learn a parameter policy in this 11 line of pseudocode. So using human interaction I, space of possible parameter theta, and a navigation stack G, you should be able to learn the parameter policy we call pi here. And then during deployment, you should be able to consult your pi to give you the optimal parameter set per time step, and then navigate with the navigation system parameterized by the optimal parameters. Of course, the key here is this line. How do we actually learn this parameter policy using human interactions? So you already know very well how to do it with demonstration. We explained this in a lot of details, right? What we did is we imposed an internal structure here for this parameter policy, something called the context predictor, mapped from robot state to the context index, and then context index into a parameter library to give you the right parameters to be used. You know that. We have talked about those in the last 10 minutes. But you may also think like robots do not usually need a demonstration everywhere. So robots do not behave suboptimally everywhere, and humans can only intervene when necessary, when the robot is about to make a mistake. So this is our second Apple approach called Apple I, adaptive planning parameter learning from interventions. So humans do not need to give the entire demonstration here, but only intervene at this yellow and red point where the robots make a mistake or behave suboptimally. Then we should be able to add another component into our context predictor called the confidence measure. So the context predictor, each prediction will be also associated with the confidence measure. So if the robot is confident, it will just pick the parameter set in the parameter library to navigate the robot. However, if it's not confident, because the scene is not intervened before or it's unseen before, we can revert back to our default parameters, like the ones given by the robot manufacturer to navigate the robot as well. So this is interventions. And some people may think, hey, I'm not comfortable taking a joystick to drive the robot. It's not safe. I'm not a gamer. I don't want to do that, right? But those people still know if a robot is doing a good job or maybe a bad job. You know the robot is not doing a good job when it's stuck at the doorway, right? So you know it's doing a good job when it's driving very smoothly. So that's why we also have this Apple E work, adaptive planning parameter learning from evaluative feedback. So in this sense, humans only need to give evaluative feedback in terms of a scalar value or even a binary value like a thumbs up or thumbs down. Even with those very sparse interaction modalities, we should still be able to learn two versions of Apple E policies. First one is the discrete version. So instead of the context predictor, we can devise a feedback predictor here and trying to maximize the feedback from humans and then use the parameters associated with this set of parameters to drive the robots. Another version is our continuous version of Apple E. Then we just use the policy network in the middle that is trying to maximize the eval feedback and also trying to come up with the parameters using an actor critic setup, as Chris has mentioned earlier. So what about no humans at all, right? Can we also learn to improve navigation performances? So this is where reinforcement comes into play. And of course, you probably need to do it in simulation. So this is our bond data set we talked about earlier. So we will be able to learn a parameter policy using end-to-end reinforced learning to learn this policy network so that the parameters to be used by the underlying planner can maximize our reward. So with all these different human interaction modalities, we also put them together in a cycle of learning scheme. So by cycle of learning scheme, what I mean is, each interaction modality of one human for one scenario should not be only targeted at improve one scenario alone, but any future deployment scenarios in a cyclic and in an iterative fashion, so that the robots can improve within its lifetime. And of course, one single robot's lifetime is not our ultimate goal. Eventually, there will be lots of robots being deployed in the field with lots of different users. And all these robots are from the same robot manufacturer, already have a very natural infrastructure to, for example, share experiences, to crowdsource interactions, and to transfer knowledge. And within this robot manufacturer, so computation is not really an issue because they have lots of compute in the factory, right? So then we can utilize the cycle of learning to crank the learning inside so that all the robots in the field can learn from all these different users, as a fleet. So this is, our future work. So we want to work on this when we have lots of robots in the lab and we have lots of humans interacting with them in the field. So this wraps up the first half of the talk. So we want to utilize all these even non-expert humans around the humans in the non-expert humans around the robots in the field to improve our robot navigation performances using Apple. So I guess I can hold questions to the end. So let's quickly jump into the second part of the talk. So here we're gonna trying to introduce a few infrastructure and also methods to address the challenges associated with social robot navigation. So first, I want to introduce two different data sets we collected so robots can learn from human demonstrations to learn socially compliant navigation. This is called SCAN-D, socially compliant navigation demonstration dataset. So it's 40 kilometers or 8.7 hours of real-world human tele-operated demonstration of socially compliant robot navigation behavior on UT Austin campus. So we have 138 trajectories collected over 15 days, and we have two different robots in the dataset. One is a Kurt plus Jackal. You have seen it before. So that's a wheeled robot. We also have a Boston Dynamics Spot, which is a legged robot. Both of these robots are driven in indoor and outdoor environments at UT Austin, and by 4 different human demonstrators to give you a different style preference. And we also provide some course labels of social interactions in the data set to give you an idea what is going on in each of those navigation demonstration trials. So this is a pretty decent amount of data for us to learn something out of it, right? But what if you want more? More data is almost always going to be helpful, right? So one problem with collecting social robot navigation in the ScanD way is it still takes some effort to bring the robots to different places, set it up, collect the data, and go back and port the data, right? It's still not that easy to collect all these data. This motivates our second data set called Musuhu, multi-model social human navigation data set. So here, we actually want to collect data from social navigation experts, so humans ourselves, because humans are very good at navigating through highly dense human crowds without any problem, while also being efficient and also being polite, being socially compliant. So what we did was we constructed a sensor suite on a ski helmet. And we have all the commonly available sensor modalities, 3D LiDAR, stereo and depth cameras, microphone array, IMU, and also 360 cameras on top, right? So we just need to wear this helmet, walk around any public spaces, and let all the data streaming in, right? This is why we have a much larger data set compared to ScanD. We already have 100 kilometers, 20 hours, 300 trials, 13 humans data, and we are still collecting those data. For example, we collected this data. This is in the National Monument, underneath the National, the Washington Monument in the National Mall in the Washington, D.C. area. As you can see, lots of tourists here. And this is called Adams Morgan area. That's a bar area in D.C. So this is actually a Saturday night. So when we collect the data, we notice the social interaction during navigation during a Saturday night in a bar area is very, very different than normal. Then, we are still collecting more, and we are also looking for partners to collect more data with us, because what we think is this is American, the US culture, right? So we want to make our data set even richer, because social navigation interactions are following different underlying social norms at different cultures. For example, if you drive on the left instead of on the right, for example, in the UK, for example, you have a more contact tolerant culture compared to the contact averse culture in the US. So if we can collect data worldwide, then we will be able to adapt all these robots into different underlying social norms very quickly as well. So after the data sets, we are also going to talk about how can we enable standardized evaluation to evaluate the social robot navigation policies or method. So this is a protocol we developed with Google Robotics. So in this protocol, we designed basically 8 very commonly encountered social navigation interactions, including frontal approach, intersection wait, intersection gesture, narrow doorway, and blind corner. So we pick locations in our buildings. This is one of the Google research buildings here. So where all these interactions will take place very naturally in your day-to-day life. And to gauge, how good or how bad the our robot's navigation performance are. So we actually also design a questionnaire so that humans can fill in this questionnaire to tell us about their subjective opinions towards the navigation performance they have observed or they have interacted with the robot. So this is another, I would say, a resource available for us to conduct social robot navigation. It's a huge effort from lots of social robot navigation researchers all around the world. So I want to acknowledge all their contributions in this. So I won't put their photos at the end of my talk, because that's a lot of photos to Googling around online. So I just want to acknowledge their contributions here. So in this paper, we provide 8 principles for us to conduct social robot navigation research, including safety, comfort, legibility, politeness, social norms, agent understanding, proactivity, and contextual appropriateness. So we have a lot of detailed discussion of how these principles should be applied to social robot navigation research. And in addition to all these principles we talked about in the last slide, we also give a bunch of guidelines when you're trying to develop your social navigation algorithm, and also when you're trying to evaluate your social navigation algorithm in terms of experiment design, which metrics do you use, what are the common scenarios you want to define in your experiment, and what are the available benchmarks, data sets, and simulators for you to conduct your research as well. So now we are done with a bunch of infrastructure we can use to enable our social robot navigation research. So here we are going to talk about 3 different approaches we have been trying to improve social robot navigation to address the challenges from all these non-expert humans in the field. So here I'm going to make 3 assertions to introduce the 3 works. So first is social robot navigation is more than classical navigation. I think most of you would probably agree with me, because that's the reason why we study social navigation in the first place. It's not just obstacle avoidance anymore. Second, social robot navigation is not only geometric, again, not only obstacle avoidance, but and also getting to the goal. It's also, but semantic. We need to observe social compliance. We need to look at the underlying social norms. So that's geometric, semantic, and even more. And third, it's not really assertion here, it's a question. So is social robot navigation really beyond what classical navigation systems can do? It looks like a little bit contradictory to the first one, but I will explain those in a few minutes. So for the first assertion we made here, we introduced a work called Performer MPC. Again, that's a work with Google Robotics and Everyday Robots. So it is MPC with real-time transformers to go beyond just classical navigation. So the second work here thinks, social navigation is not only geometric, but semantic and more. We want to look into how encoding multi-model perception can help with social compliance. We actually run a big study to look at if RGB and point cloud can help with decision-making during social navigation. And the third is something called targeted learning. So we want to learn only when classical system fails. And I will also show you some stats about really, is social navigation really beyond classical navigations can do. So first work, Performer MPC. So thanks, Chris, for already introducing MPC, right? Model predictive control. You have, a cost function you design. You try to minimize using some algorithm. So that's what Chris designed, a regular MPC setup. So this is what a regular MPC setup will give you during a social scenario. For example, this blind corner. So the regular MPC will plan the most efficient, shortest path, and also minimal time plan to cut through this blind corner. So without anticipating, there may be some human from the other side of the blind corner and risking bumping into the human. So what we did in our, what we wanted to add social compliance into the MPC so that, the robots can actually anticipate by going wide, so that maybe there's someone in the other end, so I don't want to bump into the human, so that I can go a little bit wide, compromising my efficiency, shortest path, and also time, right? So this is the social compliance behavior. So this is roughly a architecture of our Performer MPC setup. So what is a Performer? Performer is a low-ranked version of a transformer, a very, very efficient version of a transformer that can be run on onboard the robots, on GPU or even on CPU if you really want to optimize it. So this is our Performer MPC setup. Well, this is the regular MPC. Usually MPC taking in some engineered, manually designed cost to minimize and then produce trajectories. What we did was we use a performer model in here, taking some context information, and then produce a learned cost. That learned cost is including all the social compliance information necessary for the MPC to make navigation decisions. And then by adding up the learned cost and the engineering cost, MPC is able to produce trajectories in order to imitate a human demonstration. So this is in an inverse optimal control or inverse reinforcement learning setup to learn this Performer MPC. Look at the performance of Performer MPC here. So here we show the regular MPC, Performer MPC, and we also show an explicit policy, which is basically behavior cloning, to explicitly regress the state to actions here, to give you an idea. So as you can see, Performer MPC learns to go wide at this blind corner, avoiding even the center here, even though this is the shortest path. While here, the regular MPC bump into the human many times. It's almost collided with the human. It's neither safe nor socially compliant. And if implicit policy learns to go wide here, but the problem was it's not explainable, it's not safe, eventually it actually passes the goal and almost collided with the wall and need human intervention. Another example we have here is called pedestrian obstruction. So because the regular MPC is optimizing on cost, which considering the goal is right here, which is right behind the human, but there are some conflicting signals from reaching the goal and also obstacle avoidance. That is why it gets stuck at this local minimum here. And using Performer MPC, we will be able to learn to shape the cost landscape so that the robots knows go around. Similar problem happens again for our explicit BC policy. So it learns to go around, but eventually it fails to reach the goal as well and need human interventions to avoid a collision with the wall behind. So that's Performer MPC. And then another work I want to briefly talk about is called Learning Social Robot Navigation with Multi-Model Perception. So here, because we talk about social robot navigation is beyond just geometry, right? So it's also semantic and even more. So most of the onboard robot perception systems utilizes some perception to informing a social robot navigation decision-making system and to produce some decisions. For example, in terms of a global planning system, that produce a global path, or in terms of a local planning system giving you raw actions, maybe linear angular velocity to be executed on the robot. So most existing systems are really rather unimodal, either taking RGB image or taking LiDAR point cloud, right? All these are unimodal input to inform your decision-making system. So what we did here is we want to see whether adding multimodality into our navigation system can actually help in an end-to-end learning-based paradigm. So this is the architecture we designed. So nothing fancy here. It's just a regular, like I would say, like neural net. What we did is we taking RGB input and we take the point cloud in both heads. One is RGB encoder, one is point cloud encoder, and going through a few like recurrent neural net. Of course, you need to concatenate that with the navigation goal, and then you feed that through. What is special, a little bit special about this paradigm is, we also impose some internal structure to mimic our navigation system. So in here, in the middle, we actually introduce a loss function only over the global path. We enforce the output of this layer is gonna be the waypoints on the global path, and we're trying to enforce to minimize the loss here. And then in an end-to-end manner, at the end, we're also trying to minimize loss between the raw actions regressed from the model and, from, for example, our demonstration in the data sets. So here I want to briefly show you some results to let you know what is the benefits of using multi-model perception here. So this is the loss curve during training on test data. So those are unseen ScanD trials in our ScanD data set. So green is multi-model, blue is point cloud unimodel, and brown is RGB unimodel. So one takeaway here is green is always the lowest. That is not really surprising because multi-model should have more information content than unimodels, right? But I want to point out one interesting finding here. So if you look at the scenarios we describe on top of each of those blocks, from upper left with traffic, with then again traffic, all the way down to the lower bottom, so large crowd, hallway with and again traffic, you can see a rough increase in terms of navigation difficulty. You can see more and more humans are involved in these difficult scenarios. So at the same time, you can also see an increasing gap between the green and the yellow and also the blue here. So what does this mean? This means multi-model perception becoming more and more useful when the navigation scenario become more and more difficult with more and more dense human crowds in the field. So this is also a very interesting finding. So multi-model perception really shines when to deal with very difficult social scenarios. So we also put our loss curve for the local planning. So nothing too interesting about local planning, very similar trend. So green line is the best, outperforms the blue unimodel point cloud, which further outperforms the brown line here. Okay, so we also run our model on board a CLAPAS robot, so to run a human study. So we run our multi-model model, the point cloud unimodel model, RGB image, and MoveBase is the classical navigation system using point cloud only, right? You can see in this video, so multi-model and point cloud are both able to address these three people frontal approach very easily without any collision, and also get to the other side in a more or less socially compliant manner. While using RGB image, it didn't work very well, almost collided with this person here, and we have to manually intervene to stop the collision. So MoveBase is very good at dealing with static obstacles, but when the obstacles start to move around, it may not be very robust. It also performs poorly on our scenario. We also applied our multi-model network in real-world scenarios as well, in terms of one human frontal approach interaction and also two human interactions in terms of frontal approach, diverging, and merging to one side. You can see this multi-model network is able to address all these scenarios pretty efficiently. We also use our questionnaire to gauge the subjective opinions of all these test subjects and see how they perceive the social compliance. Roughly speaking, our multi-model perception pipeline achieves the highest social compliance in all these different questions. Okay, so the last work I'm gonna talk about is called targeted learning, a hybrid approach to social robot navigation. So here, the motivation is after we collect these two data sets, we ask ourselves the question, is social robot navigation really beyond what classical navigation system can do, right? Looks like a very trivial question. Probably yes, that's why we need to study social robot navigation in the first place, despite decades of experiences in classical navigation, right? But how are they really different? Let's look under the hood to understand how classical navigation fails in terms of social navigation. This is one example we picked from the ScanD dataset, so cutting across the queue. So this is the RGB visual feed to give you an idea what is happening. So food truck, people are waiting in line to get food. And on the right-hand side, we show the perception of the robot. So black is free space, white is the obstacles, humans or food truck or whatever obstacles in there. And the robot is in the center here, facing to the right. So we also plot two paths on this graph here. So green is a human demonstrated socially compliant navigation behavior in ScanD dataset. And the red one is we query at the same scenario, feeding all the perception to a classical navigation system. In this case, it's Ross Moore-based. So Ross Moore-based think the gap between these two humans are probably too narrow for the robot to safely pass. So it plans to go all the way around to the back of the queue to go to the other side. While the human, when demonstrating socially compliant navigation, it knows if I move slowly towards this gap, I may be able to nudge the people to give me a little bit more room so I can actually go through. So that's a major difference between classical navigation system and what a human thinks a robot should do. What is a social compliant navigation behavior? So that's another example, a narrow sidewalk. So there's one human, oncoming human, right? So again here, Moore-based thinks, okay, there's some human coming, I should avoid it. So it's actually planning a path to go off the sidewalk, to go on the pavement to avoid. While the human demonstrator knows in this scenario, since this is a pretty narrow sidewalk, even though the human comes from the other side, even though I have to be very close to the human, it is okay. I'm not really violating any social norms because I should stay on the sidewalk rather than go on the street. So the last example here is in a cafeteria, so waiting at a congested area. So the human demonstrator knows, okay, that's congested, but if I wait here for like a few seconds, it will clear up and then I can go through. While again, similarly for Moore-based, you think, okay, this is not gonna be a feasible path. I'm gonna go all the way around to go from the other side. So those are a few examples showing you, social robot, so classical navigation systems are not enough to deal with this social robot navigation problem in the wild, right? But of course, all these three scenarios are cherry-picked. So we picked this to show you, hey, classical navigation systems are not enough. But how are they really, good or bad? So let's quantify the difference between classical navigation and socially compliant navigation first. Here, I want to introduce the metric, which is a very simple metric called Hausdorff distance, right? So these are two trajectories, red and green. So if those trajectories look very similar, then the Hausdorff distance is very low. While if you increase the Hausdorff distance, that's corresponding to an increased gap between these two trajectories. Just to give an idea. Let's just say, okay, within 1.0, these two are very similar. Let's say that they are almost the same. And beyond 1.0, those are very different. Then, ScanD gave us an opportunity to look at every single scenarios in the data set, how this distance actually varies using different planners. So we have used a bunch of planners, and we plot here, this is the cumulative distribution function, or CDF curves, for each of those planners in different colors, right? So here, x-axis is the Hausdorff distance, while the y-axis is the percentage inside, all the ScanD scenarios, where the planner will give you a Hausdorff distance that much away from the human demonstration. So that may not be clear, but let me explain using one example. So this is a Ross Moore-based, our favorite Ross Moore-based, showing blue here. That's actually the best performing classical planner in all our case here. Only these are classical planners. I will explain what these two are later, right? So we want the curve to be more like this. More like this will be better because that means at 1.0 Hausdorff distance, we know 80% of the social scenarios in ScanD, Moore-based is able to produce less than that much Hausdorff distance compared to the human demonstration. So meaning Moore-based can resemble the human demonstration in 80% of the cases in ScanD. That is actually not a too bad a value, right? 80%. There's only 20% which it does not perform very similar to human. That's probably the three scenarios we showed before, right? Like waiting for a congested area, a narrow sidewalk, and also this passing a stationary queue. Those are those scenarios here. So one way we can deal with this problem is using, for example, end-to-end learning. For example, using behavior cloning. So we call BC here, which will show us this orange line. So we train a policy on a neural net to regress from the robot perception to the human demonstrated actions, and we show the results here. So this is actually a very, very good performance, right? So this is within same 1.0 Hausdorff distance, almost BC can produce the same navigation behavior in almost 100% of the whole data set. So the problem is probably solved. Let's use BC. BC is the best method. It will imitate the human in 100% of the scenarios. But wait, this is too good to be true. Indeed, because this is a navigation, this is a machine learning setup, right? Machine learning, you not only need to deal with in-distribution data, but also out of distribution. So in out of the distribution data, however, now let's look at the orange line, BC again. We still pick the 1.0 Hausdorff of distance, and apparently it drops from 100% to like 70%. That's a pretty big drop. That means the BC is somewhat overfitted to the in-distribution scenario and doesn't perform well in out-of-distribution scenarios. But one very good thing here is let's look at this blue classical move-based line again. You can see 10%, more than 80%. So move-based actually is not affected by in versus out-of-distribution, which also makes sense. It is not a learning-based method. It doesn't even look at the data. It is a classical, for example, MPC-based planner or a sampling-based planner. So it is even better than out of distribution than in distribution. This is also expected. So these contrasts here give us some insight about, hey, maybe we can do something better here. So actually, we should be able to utilize our blue line all the way up to this point. That's the point where the orange line overtake the blue line. This point, let's switch to use the orange line. So let's use move-based to deal with the 80% of the scenarios in ScanD, and only let the behavior cloning, the learning method, to deal with the leftover less than 20%. So what we want is this hybrid line here, which is showing in green. So the hybrid line will be able to achieve the best performance both in distribution and out of the distribution data by bootstrapping on both the blue classical navigation system and the learning-based navigation, the orange line here. So the method is very, very simple, just targeted learning. So if encountering one social scenario S, if you expect classical navigation is good, then just use the classical navigation system. If not, then you use your behavior cloning or any learned navigation systems, right? So this classification is very easy. You just train a classifier on labels based on a Hausdorff distance threshold, for example, 1.0. And then you can train a supervised learning using behavior cloning, with only scenarios where classical is not good, right? So it is a very, very targeted learning. It's a very small data set, only 20% of the ScanD data set, and hopefully it will be able to learn very well, and hopefully it will also generalize very well. So we put this hybrid learning approach on 2 different robots as well and conduct experiments on 2 university campuses. We use this wheel jackal at our university, GMU, and also the Boston Dynamics Spot at our collaborator, UT Austin. So as you can see, we have the 3 different approaches here. The classical approach, the blue line, and the hybrid approach, our green line, and the BC, our orange line here, right? So you can see classical and hybrid are mostly the same, I would say in most of the cases. And the only switches to the hybrid only switches to BC when necessary, when it thinks the classical approach is about to fail or is about to give you some socially uncompliant behavior, right? While the BC, on the other side, you can see in the Jackal experiment, it's failed many times by colliding maybe the door or losing the goal. Although it somewhat gives you some socially compliant behavior by going around the human, but it's not really that efficient. So this is the spot experiment in UT Austin as well. Very, very similar results. So we run our study again and show the results on the right-hand side. This is the same questionnaire I showed earlier, right? So people filling these questionnaires, and we do some statistical analysis, draw the mean and the standard deviation of all the responses. As you can see here, the hybrid line is always slightly higher than the others. We also put all the results here to give you a rough idea. So that's also another human study we did with all these different planners. Okay, I think these are the 3 methods we talked about to address the challenges in terms of social robot navigation. And don't forget about the infrastructures we introduced earlier, like the data sets, principles, and guidelines, and also the protocols to help you to develop your own social robot navigation research. So with this, I would like to conclude the talk. So just to recap, as we talk about both challenges and opportunities caused by non-expert humans in the wild on mobile robots performance. We utilize Apple so that those very easily available non-expert interactions can be leveraged to improve robots performance. And we talk about data sets, protocols, principles, guidelines, and learning methods to address social robot navigation challenges. And of course, all these are not my own work. I also want to acknowledge my collaborators. So Peter Stone at UT Austin and Joyce D. Biswas at UT Austin, Robin Murphy at Texas A&M, and also Howie Choset at CMU. And I also work very closely with Google Robotics. Now it's called Google DeepMind after they rebranded, called GDM. And also that is actually my previous employer, Everyday Robots, or the late Everyday Robots. The project is canceled now, unfortunately. So those are my collaborators there. And also all the accessmen and accesswomen and the robotics lab, which have done majority part of this work. I will be happy to take any questions.
Yeah, so there.
Thank you for the talk. I was wondering, in your hybrid approach, this switching that you described globally of behaviors, is it that at a step action, like in real time, it chooses which policy to do? And like, have you observed the switch rate, or like, is it following the same strategy for a while and then switching, or is it kind of hectic? Or
yes, that's a very good question. So it is in real time. We do the classifier every time step and decide which output to use. It is indeed hectic if you're using the raw classifier result. That's why there's some massaging you have to do, filtering out all the high frequency noise. That's what we actually did. We implementing a low pass filter, and then don't switch very often, because it doesn't make sense for you to do classical at this frame and BC at the next frame and then switch back to BC immediately, right? So that's some engineering trick we did in the implementation.
Thank you very much.
Yes, so I have a question. Basically, some of the examples you showed, for instance, the latest ones where you do the hybrids and then you demonstrate, you did some experimentation. From what I could see, those people are roboticists, right? Because they don't even take attention.
Yes.
But when you actually start deploying these algorithms in real settings, humans are not familiar with these robots, like a dog-looking robot walking around me. My perception of it and my movements and behavior will be very different.
Yes.
And also the embodiment matters. If the robot is very big,
Yes.
the amount of space, people will be scared, right? They actually will probably run away and not try to. So there will be no social navigation. So all these algorithms, how do you envisage, taking them out to really like real world settings?
Yes.
Thank you.
Yes. That's a very, very good point. So all the videos we show, those are our students, roboticists, right? So in our experiment, we did include some other non-robotic students, but I would say in general, those are engineering students. That's the easiest, pool of participants we can recruit. But I guess the short answer is I don't have a good answer for you, because those are indeed the problems. So what we want to do, so we are actually designing that experiment now, is we want to do a long-term in the wild test with our robots. For example, all these food delivery robots you have seen, we have the capability to deploy our robots on campus as well. One idea we have is we can deploy those robots on campus for a while and try to send out the questionnaires to all the students on campus who have interacted with the robots. And then that's going to be a very difficult experiment to run, and it will be very long-term. Then we can also compare different algorithms. This month we deploy algorithm A, next month we switch to B, and compare the responses on our questionnaire on these two sets. Yeah, but yes. Yes. Yeah. Yes, that's also a very good point. And also the GMU students is also somewhat polluted because they are very familiar with all these delivery robots. So that's another different thing to think about. So I would say, so another thing about when we collect data is when we drive the robots around, so the interaction between the robots and the humans are not really socially compliant because there's a lot of other factors at play. Human will come up to us as, hey, what are you doing? Can you explain what is the robot doing? Especially when we are wearing our very, look interesting helmet when we walk around in public spaces. Yes. Yes. Exactly. Yes. Yes. Yes, so all these things are, I would say, it's definitely a limitation of our current approach. But I guess social navigation is also evolving, right? How people perceive robots, that will be different today than in 2 years. And how can we deal with that? So that's definitely an open challenge.
Hi, can you maybe go back to the multimodal perception architecture?
Yes. This one.
Yeah. So you're using a recurrent neural network, right?
Yes.
With a transformer.
Yes.
So I'm confused about that because like a recurrent neural network, its main disadvantage is that it cannot be trained in parallel. It has to be trained sequentially. While the transformer, its advantage is the ability to be trained in parallel. So by using together the RNN and the transformer, you lose the main advantage of the transformer. So why do you have both?
So I think that's an empirical decision we made. So I think basically based on our different choices, we figure out using RNN for the encoder head, and then eventually at the end, using the transformer, it performs the best, at least for our experiment. I guess I do not have a, I would say, theoretically sound answer for you. That's just based on empirical experiences.
Okay. And the next question would be, what are those real-time transformers? Like, why don't you use regular transformers? I guess it can be used as well in like real-time applications.
Yes. So basically, this is the performer MPC work you talked about, right? So of course, you can use regular transformers if you will be able to run that on board. So the problem we have is, assuming you don't have a GPU on board, how can you query these large networks very quickly, right? So in this work, we are using, I believe it's not CPU only, it's also GPU, but we actually have a study on how a regular transformer versus our performer and also different variation in between can give you real-time performance. We have a benchmark in the paper to tell you about the details. You know, I guess the main thing here is about efficiency, right? We don't want to use large models on board the robot. And remember, this model is not giving us direct actions. It is only a small piece in our MPC setup. It will only produce this learned cost for you, and you still need to run your, this is the IOQR setup, MPC, so iterative linear regulator here. So lots of computation are here, actually. So eventually what you need to think about is, you know, how much compute is available for you to consume the context into some learned cost. So because this work is done with everyday robots, another very important thing is, you know, we like to say how much compute you have on board the robots, right? So but one question we ask in an industrial setting in everyday robots is not how much compute you have on board. It is how much compute you have assigned for you to do navigation. Because we do have very powerful GPUs on board the robots. It's Google. We have GPUs, we have TPUs, right? But I would say 95% of the compute will be used for like heavy perception tasks, running semantic maps, running object detection. And what are available for our navigation computation is very, very low. So that's our job to make it very, very efficient. So that is the motivation of using performer rather than a full-scale transformer on board.
Okay, so do you maybe know what's the difference in performance between like a regular transformer and a real-time transformer?
So I would refer you to a paper from my co-author Christoph here. So they have, in the performer paper, I think it's an iClear paper, like 3 years ago, they have run a study on that.
Okay, thanks.
Yeah, thank you for your very clear presentation. Because you said you used a small model, and also in general, I'm curious about whether in the research project you guys have also taken into account the environmental impact, for example, the energy consumption and all that. And if in your like soon to be published paper, if you're gonna reveal it, some metrics for that.
You mean energy consumption in terms of motion or in terms of computation?
Computation firstly, but also let's say maybe the embedded emissions which are used to well make the hardware and end of life, like an LCA maybe. Like, are you thinking about it?
Yeah. So we have a recent work, I didn't talk about this, called VAMP, Vision Action Navigation Pre-Training. That is trying to address the issue you mentioned. Because, you know, we have lots of large neural net which are pre-trained using extensive resources, right? But those may not be appropriate for, like, for example, our downstream navigation task. We have a work is trying to improve the pre-training efficiency, considering all these, you know, as you can see, like energy consumption, like how much GPUs you need in order to make our pre-trained network more appropriate to all downstream navigation tasks. So we show that we are only using like 0.08% of, for example, the image data set. And then we will be able to perform very similarly as that. So that is one effort. I didn't talk about this here. One effort from us trying to, you know, make it more like environment friendly, I would say.
Sure, thank you. And also, I mean, it's just a request. I mean, if people are reporting their energy consumption, or I mean, it's kind of helpful for other conferences like ICT for sustainability. You know, if you just report some simple metrics, it's just easier for other researchers to kind of just get the overall picture of the environmental impact of research in a particular country or an area. So yeah, thanks.
I think that's a very good point. And also, I would say, as academic labs, we are probably not contributing too much to that, because this is the work done by Google. You know, I can tell you how much compute I used to perform that, to compute that performer architecture. You know.
Thank you very much for the talk. And I have a few questions. First, you presented the Apple approach. In the Apple approach, can you share what is the transferability of the performance of Apple approach in different environments?
Transferability, right?
Yeah.
Okay, sure. Okay, I guess I'm not. So for Apple, we have, you mean one single Apple approach or the entire cycle of learning scheme here? So the whole idea of Apple is trying to transfer in different environments.
Okay.
If you don't, if you're not able to transfer what you do, you ask a human for help. And the cool thing about Apple is that human does not need to be a roboticist. That human does not need to know how to program the robot or how to fine-tune the parameters. What they can do is pick whatever interaction modality you think you feel the most comfortable with. If you can drive a robot, go demonstrate. If you cannot demonstrate, you can intervene if you feel necessary. Or worst case, you give a thumbs up, thumbs down, right? So using that, you should be able to adapt to different scenarios. That's the whole purpose of this whole Apple paradigm. By using this parameter policy on top, which is learned continuously from different human interactions, you will be able to adapt the underlying navigation system. So the navigation system can adapt to different real-world scenarios.
So if it is not able to perform well, we have to kind of guide it to perform well?
Yes, so that's the key here, right? Because our classical navigation systems is not guaranteed to work very well everywhere, right? But when it doesn't work very well, what is common practice now? Robotics have to go there, sit down, SSH, parameter like tuning, right? So that's what we are very familiar with. Not everyone is able to do that, right? So that's why we can use non-expert humans to do this process.
Okay, thank you, Xuesu, for all this impressive work. With this, we are finishing the session, but of course you will be around, so just ask your questions.